Good afternoon, everyone. Thanks for coming. It's my great pleasure to introduce this afternoon colloquium speaker, Jana Giceva. Jana is a PhD student in the computer science department at ETH Zurich. She's also the 2014 recipient of a Google European Fellowship in Operating Systems. She does really exciting work in system support for data science, especially looking at how can we better build systems to truly explore, exploit the modern and even future hardware trends. So welcome, Jana.
Thank you, Magda. Thank you for hosting me. So my name is Jana Giceva. I come from the Department of Computer Science at ETH Zurich. And today I will tell you about how we can customize the system stack for data processing, why it's important, and for example, what are the benefits we can get from them. For instance, throughput increase by a factor of 7. Now, before I enter the more technical part of the talk, first I wanted to tell you a bit about myself. So I'm a systems person. That means that I enjoy designing, implementing, and working with systems. And in my primary area, it's been building systems that address the challenges of data processing workloads on modern machines. And I see myself as bridging basically 3 different areas. So the data processing, operating systems, and a bit of hardware architecture. So I like looking at problems that solve performance problems where we would optimize the implementation of certain algorithms or look into performance interference problems between concurrently executing tasks and eventually understanding and modeling system behavior. Now, where does this fit in a wider context? So part of the problem is, given certain problem X, designing an efficient algorithm for it. And here, we can try to optimize for improving the quality of the answers we give to the users, or improving the algorithmic complexity, the message complexity, or even the convergence rate. Now, the second part is, how do we optimize the implementation of these algorithms to best exploit the potential of modern hardware, or modern and future hardware? And as a community, we've already experienced the importance of this stage, because as soon as we learn how to map the deep neural networks onto the GPUs and use the massive parallelism, we can now use it in a much more widespread use of use cases. And then yet the third part of the problem is, how do we integrate all of these problems in a real system where we will have to serve many users? So we have different users with their different problems that need to be mapped on certain algorithms that will be then executed on different implementations of these algorithms over a potentially common data set over a shared pool of resources. And me coming from a relational database background, we try to optimize for throughput performance. So not just solve how to execute efficiently one job at a time, but serve many thousands, hundreds or thousands of clients at the same time. Now, during my PhD, in my research experience, I touched upon areas in various aspects or various layers of the system stack. So in the data processing layer, I looked into problems or building systems for hybrid workloads that will handle efficiently and predictable performance for addressing hybrid workloads, transactional and analytical, as well as distributed query processing on multi-core machines. And then I also worked on the second part of the problem that I just mentioned. So how can we tune algorithms from databases or from graph processing onto novel hardware platforms? During my internship with Microsoft Research, I worked on the runtime system layer. And there we were looking into the memory management for stateful big data systems, such as NIAD. From the other side of the system stack, in collaboration with Oracle Labs, I worked on hardware-software co-design, or how can we design, what would a chip look like if we were to optimize it for data analytics. This is in the context of the RAPID project. However, in the rest of the talk, I'll focus on my work in the operating system layer, where I revisited a decades-old problem that exists between operating systems and databases when it comes to resource management and scheduling. And the reason why I choose to talk to you more about this area is because I believe that basically the mechanisms and the policies, the services that I talk about are not only applicable to database systems, but to other data processing applications as well. So databases and operating system, as I said, have a decades-long conflict when it comes to resource management and scheduling. And the problem was initially discussed by Jim Gray and Mike Stonebraker in the late 70s, early 80s, and then is continuously being revisited over the course of the years by many other researchers. Now, the main problem for this conflict lies in the fact that both systems initially started with the same philosophy of providing efficient access to data written in files, but it took different approaches when implementing it. And it was because they were targeting different types of applications, as well as that they were running on different types of machines. Now, with the economic advantage of off-the-shelf hardware, we no longer relied on running database systems on the database machines. And then we slowly started using databases on top of conventional operating systems on top of off-the-shelf hardware. Now, as a result, today, both of these systems overlap in many areas when it comes to mechanisms for managing these resources, but also conflicting policies about it when it comes to thread management, scheduling, paging, buffers, memory, and so on. So why is it important that we look into this problem now? So what are the current trends? So on one side is modern hardware. Machines are becoming increasingly more complex and increasing both size and complexity. We have heterogeneous resources and a plethora of different features that are continuously being added by the hardware vendors. And this is all changing at a very fast pace. And it's not only the diversity that we have within a machine, but across machines on the market and different versions that come every 2 years. Then the second part is applications and workloads. So it's no longer data warehousing that is the only type of application that does data analytics, right? So we have graph processing, we have data mining, machine learning. So these are all workloads that are very data intensive. And they stress the memory subsystem just as much as they stress the CPU. And at the same time, they are all driven by having predictable performance for the end user's experience, and as well as efficient resource utilization. And last but not least are the deployment trends. So looking at server consolidation, virtualization, multi-tenancy, moving to the cloud, databases can no longer assume to be the only application that runs in the system and has exclusive right over the resources on the machine. So they're increasingly more often deployed alongside other applications and will still have to meet the similar type of requirements from the workload, in this case in a noisy environment, which makes it a lot more challenging. So what are the problems with existing approaches? So first option we have is that we rely on the generic operating system policies. The problem is that the operating system typically optimizes for some system-wide objectives, right? And then they try to achieve good load balancing of work over the cores or on the memory controllers, right? And rarely do they try to, almost never do they try to link and how their decisions actually impact the performance of the particular systems that run on top. And the problem with that I show in this graph, where we show the latency of a graph processing algorithm. This is an experiment done by Stefan Kessler in his PhD thesis last year, where he shows the difference in the performance of the system when it relies on the generic OS policy for memory allocation, which is the first touch memory policy, memory allocation, or as opposed to an optimal, or let's say hand-tuned, or from a compiler that understands the access patterns and the data structures and so on. So as you can see in the graph, we're talking about a difference of a factor of 4 in performance when you would rely on the generic policies as opposed to optimal or hand-tuned ones. So what is typically being done then in the research database community, at least, is we're working around existing OS policies. What I mean by that is that we try to understand on what the operating system will do, and we implement the algorithms and we build the database based on our understanding. For instance, if we know that the OS will do the first touch memory allocation policy, and we are implementing a parallel operator, we're going to partition the data, let every thread touch the data that they will be working with, then that will ensure to be allocated on the corresponding NUMA node, and then the subsequent processing will be local to that thread. Now, the problem with this type of approach is that such optimizations can easily break when there are changes in the operating system. Right? And to give a concrete example, here I show the throughput of a database aggregation operator in tuples per second. This is an experiment done by Inge Müller, so he's a new postdoc in the systems group. And so when he came last year, he wanted to reproduce the numbers of a PhD student that recently graduated. So he's using, the same source code, the same input data set, the same machine. Everything is the same except the Linux, which the kernel we updated in the meantime. And we could not reproduce the numbers. And it's continuously, a third drop in performance and a bit less stable. And the difference was that in the newer version of the kernel, they added a NUMA balancing feature, which is enabled by default. And that one monitors on how the access patterns are like and then migrates the pages around. Now, this should, in principle, improve the performance of many applications that were not otherwise optimized for, the memory system. But in this case, it just hurts our performance. And you can imagine this is just, a simple algorithm, one database operator. And you can see how complex things can get if we have built a very big system and rely on our assumptions about what the operating system will do. So then the last one is to choose the policies. And then this is really the library OS approach or the two-level scheduling. So one can easily argue that if we were to use libnuma and pin the memory and the threads, then we're going to solve the problems that we have in the first two cases, and this is true. Now, the danger with this approach is that you actually give control to an application, in this case the database, which doesn't know the runtime system state, right? So whatever decision we make that works well in an isolated scenario can no longer, be the case when we run in a noisy environment where we share the resources with someone else because we're not aware of it. If you let every application pin the threads to wherever they want, it may be that they start sharing a core and then their performance is immediately affected. So the biggest problem is that there is a big knowledge gap between the database and the operating system and what they know. So a database knows the application requirements and the characteristics, the data structures, the access patterns, the data layout, all the cost models. The optimizer has so much valuable information, but all of that is just invisible to the operating system. And similarly, the OS knows about the hardware properties as well as the runtime system state. So what other applications we have in the system, how the resources are being used, and what are these applications' requirements in the near future. So, part of my work addresses this semantic gap that exists between the two systems. So if I were to sketch my research contributions, and this is basically outlines the rest of my talk, is the following. So I look into in the first part, I look into this problem of the knowledge gap that exists between the two layers. And here I answer questions such as, what is the knowledge that each of the two systems have, and where should that reside? And what type of information can the database pass on to the operating system so that we can do better in terms of resource management and scheduling for the policies? But also, how can the OS help with the hardware complexity, diversity, as well as with the runtime noise in the system, so to speak? So in order to do that, I introduced a policy engine in the operating system that can now reason about the application's requirements And then there is a resource profiler that can monitor. First, you can basically detect what are the capacities of the resources and then monitor their utilization, and then feed the policy engine with more information so that it can have more informed decisions. And then I show how with a declarative interface, multiple components of the database system can benefit from bidirectional information flow between the two layers. And then the second part complements it, because it's not just addressing the knowledge gap. It's how can we customize now the OS for data processing. And here we're looking into several problems. For example, the complexity of modern parallel applications, especially data processing applications, and then identifying what are the suitable mechanisms and services from the operating system to address these requirements, and then how can we enrich the interface so that we can use them. Again, so as I said, this is really the outline of the talk. So in the first part, I talk about the policy engine. So the policy engine in the operating system is not, it's building up on existing work. So for some of you that know, Windows already has a knowledge base internally that keeps like a key value store of information about the resources that it has, that it needs to manage. And similarly, in Barrelfish, there's the system knowledge base, and Barrelfish is the research operating system that I built, that I used for my work. Adrian Schubach, in his PhD thesis, designed the system knowledge base, the SKB. It basically it uses Prolog and a rich knowledge base to capture the properties of the resources, hardware resources that we need to manage. And then there is an optimizer and a SAT solver that allows us to use to basically reason about the information about the resources that we need to manage. So I extended it so that we differentiate between system-level facts that we keep in the policy engine and application-specific facts. Now, the system-level facts are initially populated when we bootstrap the system. So we look into the hardware by looking at the specs, and we populated about CPU information, the interconnect, the caches, and so on. And then, via declarative interface, we allow the database, in this case the storage engine, to push some properties about the workload that it executes. And this is something that the operating system can immediately understand. Do I have a CPU or memory bound? Am I okay with sharing the resources? What is the minimum number of cores that I need, and so on. And the most interesting part is these application-specific facts. So there, I push information or terminology that is really only understandable by the application, in this case, the database. So we push information that describes the workload, in this case, number of queries or requests that we are handling in a batch in the storage engine. We try to describe the data store, right? So the database does not really think in terms of only bytes, right? It thinks about tuples and the size of each tuple and so on. And then what is the service level agreement for response time that we need to meet for the other layers of the data processing engine. Now that we have the database terminology in place, we push down cost models. And now what these cost models are, they basically add meaning to the system level facts that the OS understands, resources like cores and memory and so on, and we add semantic meaning to them, to how they are linked with the properties of the database. So in this case, how is the response time of the storage engine affected by the number of cores that are being allocated by the operating system, given the input data set size in terms of number of tuples? Because if we were to partition the storage engine, then we do horizontal partitioning, and then every thread will be responsible for each partition. And then it depends on the number of, basically on the workload, in this case, the number of queries that we'll be executing over that partition. Right? So already this is just a simple example, but it already shows that now the OS can reason about how the response time, and given these SLAs, will be affected when we change the number of cores that we allocate to the database. So it's just it can now reason about the requirements. And it's not just one directional, so that we push information from the database down to the operating system, but I also borrow the concept of stored procedures from databases. So, stored procedures allow us to push application logic, business logic, down to where the data sits, so that we can avoid having to go back and forth of reading data so that we can make our business logic decisions. And the intuition here is similar. So we want to have part of the two-level scheduling. So part of the decisions that should be made in the applications, and in this case the database, push down to where the runtime state sits, which is in the policy engine of the database, of the operating system, and then we can use access to that information to derive how we should react in the database when certain events happen. And I guess most things will become clear when we go through an example. So here I show how we've adapted an existing storage engine, which is Crescanda is a shared scan execution engine, storage engine developed in the systems group that is motivated by the airline industry. So Amadeus is a service provider for all the airline ticketing companies. And then we have their data set. We have about 53 gigabytes, and there is a 3 seconds latency for SLA for the latency that needs to be met. And we executed on the AMD MagnaCore machine that has 48 cores. And as noise, I add another CPU-intensive task on core 0 every 4 minutes. So on the graph, I show the elapsed time of the experiment in terms of minutes. This is the bolded line of the SLA because that the system needs to meet, and this is the latency in terms of seconds. So the naive system behaves in the following way. Whenever a new task enters the system, it now starts sharing a core with the storage engine, and because they're both CPU intensive, so the storage engine of the database does a lot of string comparison, which makes it a very CPU intensive task. And so they slow down one of the scan threads. Now, because we have frequent synchronization steps, that scan thread becomes a straggler and slows everyone down. And of course, here it's a very pathological case because you remember I added every new task at the same core, core 0. So if we let applications just randomly choose cores to put, we could just continue slowing down, in this case, the same scan thread, and then the system just further degrades in terms of performance. In the adaptive case, what happens is the following. Whenever a new task enters the system, it triggers recomputation of the global, because it registers with the policy engine, so it triggers a recomputation of the allocation of resources that happens in the OS, on the OS side. So now that we added the cost model, the cost functions for how the response time is affected with the number of cores that we have allocated to the database, the OS knows that even if I take away one of the cores, it can still meet the SLA requirements in terms of response time. So it notifies the database that it should release a core, and or even a given core. So now the database needs to decide that core was already running a scan thread that was responsible for a certain partition of the data. So now we need to decide on how do we redistribute the tuples that that thread was responsible for across the remaining threads that we have available, or the cores. And then the storage engine invokes a stored procedure in the policy engine of the OS that looks at how the rest of the resources are used in order to decide where to redistribute the tuples and how the scanning should proceed. And after that is done, then it notifies back the storage engine, and the tuple redistribution happens, and then the scan resumes. And as you can see, whenever a new task enters, there's a slight increase in the response time. We pay some penalty when redistributing the tasks, but we can still meet the SLA requirements. And this is just an example of how leveraging the information from both coming from both layers can help us be more adaptive to dynamic system state. Now the second component that I introduced is the resource profiler. And the resource profiler allows us to monitor the resource usage in a system-wide scope. And this, of course, will enable us first to build more accurate machine models, because we don't only read the capacity of certain resources from the specs, but we can actually do micro benchmarks and build more accurate models about it. But also, we can monitor the resource utilization at runtime. And we also allow for application-specific monitoring for particular threads or for particular application or component of the application, and that, of course, allows us to build some resource profiles of the utilization of resources for these individual pieces. And I show how we can use this information for an already existing problem in databases, which is how do we efficiently deploy complex query plans on multi-core machines. And just to illustrate, so this is a complex, basically a big query plan that is generated by ShareDB's optimizer. ShareDB is a database engine developed in the systems group, where we exploit sharing to basically answer all of 11 web interactions of TPCW in a single global query plan. So this one has 44 operators. You don't really need to understand it. It's just that the intuition behind this is that there is a complex data dependency that exists between the operators, right? And you can already see that the data dependency graph or the data flow graph already tells you where the data moves and whether there are some blocking operator pipelines and so on. And this is very valuable information when you would do efficient scheduling of resources. And this is something that the operating system does not see, and it's something that I try to explore in the next, I will explore in the next example. So again, we try to deploy it on the same multi-core machine that I introduced in the previous example, the magni-core machine. So the way it works is that we get this data dependency graph from the query plan, and then we feed it down to the policy engine of the operating system. And then together with the resource profile of the individual operators that we measured with a resource profiler and the model of the machine, we can basically trigger a deployment algorithm that will compute a thread to core placement. And the deployment algorithm, the goal is to achieve good performance with efficient resource utilization and help us enhance data locality. So it proceeds in several stages. The first one uses the data dependency graph that we extracted from the query plan. The second stage uses the resource utilization profile for each of the individual operators. And here we focus on two dimensions, CPU utilization and memory bandwidth usage. And then we have properties of the multi-core machine in terms of model of the NUMA nodes and the interconnect. Now, without going into too much detail about what each of the operator algorithm phases do, the first two try to compute the minimum number of CPU resources that are needed to satisfy the requirements of the query plan. The third one computes the minimum number of NUMA nodes that are needed to satisfy the memory and memory bandwidth requirements of the query plan and its operators. And the final one chooses which resources should be used on the machine. So we have the deployment. Question?
I have a question. In the first example, you showed that the storage engine will actually use the interface to specify things such as cost models, and that will allow the operating system to do a better job scheduling and allocating different cores. But in this example, we're saying, well, actually, if we have some workloads, we can just run them and profile them. So how much can we simply rely on this automated profiling, and how much does the actual storage engine or other data processing system actually have to specify?
Yeah, that's an excellent question. So because coming up with not every application has these cost models. And one alternative would be to use, not to have these very precise cost models available, then we could use a resource profiler to estimate on what are the requirements, which are the sensitive resources, how intensively we use them, or how sensitive we are to sharing them. So in this case, we try to leverage the fact that often even the workload can change over time, and then having such characterization can help us better adjust to the workload changes and their requirements. Any other questions at this point? So the existing deployment approaches that we compared basically the output of the performance of the system using the output of the deployment algorithm is first the default OS scheduling, which does not understand the data dependency because it doesn't have access to the data dependency graph. It can migrate threads around and can use, in principle, the whole machine. And then the alternative is that we I call it operator per core deployment, but basically the intuition is that you have a dedicated set of resources that you allocate to each of the operators, and that will ensure data locality, but at the cost of potentially over-provisioning the system. And however, many systems are willing to do that trade-off because they want to have predictable system performance. Now I compared the three approaches with three different metrics. So in the first graph, I show basically the resources that each of the approaches uses when executing the query plan. And here we look at the number of cores. The second part is the average throughput that's measured by the database system. So it's in web interactions per second. And then we look at the latency tail. And here we look at basically the 50th, 90th, 99th percentile measured in milliseconds. So we're not interested just in the average latency, but basically on what the latency tail looks like, because this is what determines the end user's experience. And it's not just database systems that look into that. It's everyone who is working and facing users, especially in the cloud. Now, the two existing approaches behave the following. So you can see that the default operating system will use all the cores on the system because it just migrates threads around. The operator per core uses 44 cores because we had 44 operators in the query plan. Now, when we look at the performance, we can see that this unpredictability of the Linux scheduler already can significantly hurt performance in terms of throughput, and very significantly the predictability of the system in terms of tail latency. So you can see the 90th and 99th percentile are significantly higher than what we get with the dedicated resources and the operator per core deployment. Now, how does the performance of the system behave when we use the output of the deployment algorithm is the following. So we can achieve the same latency tail and the same throughput with only a fraction of the resources. So here we use 6 cores, and then you can see we lose nothing in terms of performance, raw performance, or predictability. And now some of you may wonder, well, maybe it's not the cores that matters. Can you still use the machine, the remaining resources of the machine for running something else? Maybe you should focus instead on memory or something else in terms of resources. So what I did is I parallelized or added more threads in the storage layer, and I replicated the logical operators, and then I added more load to the system, and I managed to increase the throughput by a factor of 6 without changing anything else in the system, in the database system. So it's just by doing smarter scheduling of the resources that you can boost the performance. And this was clear because whenever I was running ShareDB and similar systems with the operator per core deployment, it was already about 13, 15, 20% utilization of the resources. But we couldn't just rely on the operating system because there was a lot of penalty if we just let it use. Now, yes?
I have a clarifying question. So in the second experiment that you described, once you start to parallelize the operators, there seems to be like there will be a huge difference in the amount of data movement as we schedule the different operator partitions on different cores or maybe together, as opposed to a plan where we have maybe one thread per operator and then much less movement. So do you find that this how much this kind of data shuffling in parallel query plans affect this placement algorithm?
That's a great question. So because I didn't go into the details of the of the algorithm. So every thread, regardless if it's a parallel operator or not, will be treated differently because we would allocate a separate, potentially a separate core for it. And then when we estimate the resources, each one is treated separately. When we do the actual deployment, we ensure that threads that belong to the same parallel operator are not collocated on the same core, so that they don't interfere with one another. But that's taken care of internally in the algorithm, which I'll be happy to discuss further later on.
Sorry, question?
Yeah.
So maybe I'm not understanding the straw proposal here. So one of the aspects of the work seems to be that you're trying to tell the OS to provide it a model for what the application is doing, possibly measured model of what the application is doing so that it can do better optimization. I mean, another model that at least has been proposed is to think that the EOS does a very simple, very thin layer of resource allocation and then just lets the application do whatever it wants with the resources it's given. I don't understand where that other model would come in this diagram. Like it's none of the options that you've evaluated. So I don't know, maybe you could comment on where.
Yes, no, it's a great question. So actually this result was presented in a database conference, and it was not in the context at which I presented now, right? So it was not in the context of the policy engine and Sure, I understand. Yeah, no, so this is something that I try to address with my work, right? But definitely, so even if we let the database do the scheduling of the resources, when we try to negotiate how much we actually need in order to boost our throughput performance, we still need to determine the minimum requirements, right? So then we obviously have the data dependency graph from the query plan, and then we need to use the profiler to characterize the resource requirements of the operators, and then we can get the same thing from the database side as well.
So from an API perspective, like from a kind of then whether this work is being done at one side or the other of that, isn't that important?
It is important, especially when we put in. So what I don't say here is if we are running alongside something else, right? So the argument that I made in the beginning of the talk, because the OS has the runtime state view of the system. So if in this particular example, the ShareDB runs by itself. But if we were to have other applications, then we definitely need to have the decision in the policy engine, because that will account for how the rest of the resources are being used. So the second part of the talk, I'll focus more on how we can customize the operating system for data processing. And part of the challenges I've explored is, for example, the problem of concurrency and parallelism. So how do we decide how many parallel jobs to execute concurrently, and what is the degree of parallelism for each job? How do we solve the problem that today's operating systems do not differentiate between threads belonging to different thread groups? So, using the existing Unix-based process model, we just see a complex parallel application as one process and a lot of threads. So we don't differentiate that some of these threads may work on a transactional processing side of the system. Others may run analytical jobs, some of which differ from one to another, right? A runtime system will know the difference, but an operating system with these layers of abstraction loses that type of information. So in my work, I look into what are the required mechanisms and services from the OS side to be able to address such requirements from parallel data processing workloads. And then how do we expand the interface so that we can use it? Now, some of you may wonder, well, do we now need specialized OS support for data processing? Doesn't that conflict with my initial statement when I said databases will no longer run alone on the machines? So aren't these conflicting statements? And this is correct. For a long time, this was the reason why databases could not influence what the OS could do for them, and instead were doing things on their own. But what has happened in the meantime is that as the systems community started addressing the scalability property challenges of multi-core machines and so on, they introduced the multi-kernel model, which was presented at SSP in 2009. But there are several research operating systems that implemented it: Barrelfish, Factored OS, Cori, and so on. And what that does is that it has it spawns a different kernel on each core. And then basically this is the same kernel which is partitioned and replicated, so the OS state, and then they use message passing to keep the state consistent. And now since 2014 at SSP, there was a paper by Gerd Zellweger that allowed, in Barrelfish, that we decouple OS from kernel from cores, and that enables us to hot swap a kernel at runtime in terms of milliseconds without affecting the rest of the system. And now, initially they proposed that because they wanted to, patch kernels at runtime or maybe run a real-time kernel. What I propose to use it for is the following. So borrowing the idea of control data plane from networking, I suggest that we have a control and compute plane to how we use the computational resources available on the machine. And now the compute plane can have lightweight, thin kernels that can be customized for the particular needs of an application that we run, as well as for the underlying hardware architecture. And note that because of the hot swapping of the cores, this bound and the control plane will run the full weight operating system and decide on what executes and what type of compute plane kernels we run here. But the boundary is not really fixed because we can dynamically update the kernel and have the full weight kernel or the control plane expand and so on. Now, so what I'm going to do next is show you how we can specialize the compute plane kernel for parallel data processing. And here I diverge a bit from database systems, and I look into how we can schedule multiple parallel jobs from graph processing. And we are looking into live journal data set and PageRank algorithm on the same machine as before. And now each PageRank algorithm runs on a separate OpenMP instance, and we use the Greenmull implementation from Stanford. Now, the setup of the experiment is the following. So I want to increase the number of PageRank instances. And when I run a single PageRank, I execute it on 6 cores. And then when I want to run 2 PageRank instances, I allow the system to use 12 cores and so on. So the expectation is that as long as we have sufficient resources, the throughput in terms of PageRanks per second is going to increase linearly. What I observe is the following, right? So despite having enough resources, the throughput does not scale, and the response time of each job suffers. Now, there are many problems that contribute, many factors that contribute to that problem. First of all is, and by far the most important one, is the poor choice of degree of parallelism of the OpenMP runtime, because by default it assumes to have full control over the machine, and it doesn't link it to the properties of the algorithm that it runs or the properties of the data set that is used when executing that algorithm. And then as a result, whenever we have more than one OpenMP instance, we have oversubscription of the resources because they are not aware of each other. And then the OS needs to deal with the mess of context switching, preemption, and so on that will pollute the caches. So the solution that I propose is that we execute with no preemption. It's a bit of a extreme side, but the main idea is that we don't context switch analytical jobs, because it's not only avoiding the convoy effect that we typically see when we have synchronization heavy jobs, but because I notice with micro benchmarks that the indirect cost of a context switch can grow from 0.6 microseconds to 6 milliseconds. Just because of sensitivity of how we use the data in the caches. And this is, mind you, 4 orders of magnitude difference in performance, and almost at the same basically it's almost the same with the existing quanta of the Linux scheduler. So you may never really run at full speed if you're a sensitive job. And so the rest is co-scheduling of parallel tasks. So this is more in the area of gang scheduling, as well as this is the temporal aspect of the scheduling. Then we have spatial isolation and NUMA nodes or hardware islands, because DRAM bandwidth is the only resource that we cannot really provision and control. And then in order to have predictable performance, we have to isolate the jobs, and then we implement it as an OS service. And the way it looks is the following. So we have I call it a buslet, a kernel integrated runtime, and it's spawned on a different NUMA node for spatial isolation. We collocate tasks of the same parallel job on one buslet instance, and then we execute them until completion with no preemption. And with this, if we look at the performance of the same workload, then we can see that the throughput scales up until we have 7 instances, and then it flattens out. And this is because we use basically we use the 8th NUMA node for running the control plane where the rest of the threads are executed. The way we interface with this is whenever we want to execute a parallel job, the system just enqueues it in the system by invoking a library call. It's enqueued, then it's dequeued by one of the buslet kernels. We switch to the address space of the application and execute it until completion. Now, looking ahead, if we look at modern machines, I was just talking about multi-core machines, but then we have various forms of heterogeneity, accelerators or active DRAM, smart NICs, and so on. And then we have different types of analytics, not just databases, but we have graph processing and machine learning. And most of these challenges cannot be addressed by looking at a single layer of the system stack, be it the OS or the data processing system. And instead, it requires a holistic approach with cross-layer optimizations and leveraging the information that is available in both. And of course, we can make it even more exciting and benefit even more if we integrate with the runtime and the compiler. Of course, rack scale makes everything even more interesting and gives us more opportunities, as well as makes it more important. But what I would like to just briefly finish with is my vision for the future. So I want to have a system, as I said in the beginning, where we integrate in a system many different workloads and their requirements from many users. So we want to achieve high throughput, rich interface, and efficient resource usage. And in order to achieve that, the mission is to build a system for data analytics on modern hardware platforms. So various different types of data processing workloads, and not just multi-core and rack scale, but different types of accelerators. And so here the questions are, how do we use this modern hardware efficiently and manage it? How do we serve these large volumes of users? And if we think about it, for many years, the database community was exactly answering that type of questions and has been the backbone of enterprise industry. Now, the reason why we can no longer as extensively use it is, this is my saying, is that the existing SQL operators are too coarse-grained to capture the expressiveness that is needed by modern data processing workloads. So the idea is that we break them down into sub-operators and then expose that as, Legos that users can build more complex data flows. And then the database runtime becomes a language-based runtime that uses these as an instruction set architecture. And then, of course, we can use them as also as application kernels that enables us to, as an opportunity to also influence future hardware and what the accelerator should look like to address the needs of modern workloads. To summarize, current workload and hardware trends require a holistic approach. My approach is to exploit cross-layer optimization and influence the design of both future hardware and system architectures for modern workloads. I see myself as bridging 3 areas: databases, systems, and architecture. I aim for high-impact research. With that, I would like to conclude and happy to take more questions.
I'll try one.
So this is really interesting stuff, but it's based on relational databases and implementations. How does this generalize to other kinds of large-scale data management workloads?
That's a great question. So yes, my work has primarily focused on databases and in-memory processing within a single machine. Now, some of the insights, of course, are very helpful for other systems as well. For instance, that we can use the data dependency graph for efficient scheduling. Now, even graph processing systems or big data systems can provide that information to the underlying resource manager and exploit that knowledge to make, basically, to provide better and more efficient usage of the resources, and at the same time keep the predictability and the system's performance requirements. I start off with databases because they know a lot about their workloads, and that enables us to see on what is the useful type of information, and then we can take it for other systems that are not as insightful about their requirements and properties.
Yes,
have you given any thought to how this will kind of interact with cloud deployment and cloud scheduling services and like kind of splitting it off parts of different machines to handle different applications?
Yeah, so there are two aspects to that question. So first one, when we do the resource management and scheduling is one. Of course, then the operating system is not the entity that has the system runtime system view because it's just local to that machine. So obviously we'll have to, it's some form of runtime system that manages the resources that will take care of how the allocation is done. But we can definitely benefit by getting more insightful information from the applications and then monitoring on the local machines. And there is a lot of complementary research in this direction from the cloud computing and data center scheduling community that is very closely related to what I do. Now, of course, because they are exposed to a lot more different workloads, you can use even machine learning to capture and this is what Christina Delimitru now in Cornell did in one of her works, where they classify what are the properties of different workloads and what are their needs in terms of resources, and then how you react when you schedule them. The other part is what I was proposing with the customized kernels. When we think about it in the cloud scenario, then this is really what I believe is the future, because everything now gets deployed in containers. So if you could additionally add a customized kernel and add the security guarantees of what I was proposing, then you can already see the benefits of targeting the new stack for cloud systems or data centers. I mean, so already Docker acquired a unikernel from Cambridge, and unikernel was just for a single address space and not touching the kernel, but they can still show the performance benefits of customizing the rest of the system stack for the particular requirements of the workload. Now you can see this is a bit more general proposal that we can still benefit from these. We don't have to, as in Linux containers, create another container with different size of resources allocated to it and migrate things around and so on. And at the same time, we can customize also the kernel that runs in there. So I think this is really an evolution in that direction.
Any other questions?
I guess I have one question regarding to the specialized kernels. So or at least the way you talk about it in your talk, you mostly just use that to isolate things spatially, temporarily. Did you compare that to just, like, you can do the same thing on Linux by just throwing it into like a container that's pinned to a subset of cores and enabling real-time scheduling. Does like the special purpose kernel running these cores provide anything in addition to that, or?
No, definitely you can start. I mean, this is how I started, right? I was exploring on what would be the best way to run multiple parallel jobs in the system, and then from a database perspective, I said, okay, I'm just gonna pin cores and decide what goes where and so on. But eventually, when we have, if you want to have efficient resource usage, And for example, we have multiple, in this case, multiple applications, multiple OpenMP instances, and then there is another database that all wants to use to run parallel jobs, then you can just enqueue it in the system. And what the specialized kernel really does is just changes the scheduler. So now we no longer have the thread-based scheduling, we have a parallel task scheduling. And this is now, just capturing the missing bit in what currently OS provides as support for parallel workloads. And if you think about, modern architectures, what Chris Rosbeck did with the handling of GPUs. So he also proposed, P tasks for parallel tasks, and then having the operating system be the control plane for executing jobs on the GPU, as opposed to having the driver of the device manage the resources, right? So in a similar way, when we want to execute a parallel job, now we can decide on which type of device we would like to execute it. And now the thin kernel, this is an idea that has been already explored by the HPC community for the last 10 years, having thin kernels that can match the requirements of exascale computing and so on, and then allows them to really customize, remove the OS noise that will hurt their performance and so on. So I think we just propose making it more generally available for different classes of applications.
Great, let's thank our speaker. Thank you.